Hello, and thank you for joining us. Today's webinar is Generating More Data from Limited Precious Biological Samples. Our presenter today is Pete Winship, Technical Product Manager for Teledyne CETAC. We will be taking questions, so please feel free to submit your questions throughout the presentation, and we will address them at the end. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Pete Winship.
Hello, everybody. Thank you for the kind introduction. Hello, my name is Pete Winship. I'm a product manager at Teledyne CETAC Technologies. I'm responsible for the ASX 7000 platform of automation that we manufacture, and one of those systems is the MVX system that I'll be talking through today. The main focus today is generating more data from a limited amount of biological sample or precious sample, however you want to look at it. So I shall take you through that now. So to start off with, this is the MVX 7100 microliter workstation system, just to give you an idea of what it looks like. I'll be referring back to this through the presentation, and I'll give you a hardware tour and talk you through how this system works, etc. But before we get into that, I wanted to start this presentation with essentially a concept for today. So I wanted to, and I'm going to be referring back to this as I go through the presentation. So the idea of tailoring sample introduction processes to the specific sample volume that you'll be working with for ICP-MS. So when I say tailoring, I mean focusing specifically on the sample volume that you've got, the introduction flow rate for ICP-MS, with the aim of getting to the point where you are getting the most or the best possible data from your sample, overcoming some challenges that you might have, which I'll get to. And then you'll probably get tired of me saying this, but the idea of working backwards, which will become clear as we go through. So just a quick agenda for today. I wanted to take you through the idea of challenging and not challenging sample volumes for ICP-MS. The conventional sample introduction approaches that are available for ICP-MS instrumentation, the MVX 7100 system itself, so how that compares to those conventional systems and how it's different, and then tailoring the introduction process, and then taking that tailoring idea and applying it to an example of biological analysis. So in this case, with quadrupole ICP-MS, looking at blood plasma, and then after that I'll do a quick summary. So that's what I'm intending to go through today. So I shall start with the idea of challenging or not challenging, unchallenging sample volumes, and we'll take it from there. So if you are an operator of ICP-MS instrumentation, this is going to be very familiar to you, or probably be familiar to most, if not all of you. But the amount of sample available when doing ICP-MS analysis varies. Typically, or in a lot of cases, there is more sample than you would need. In some cases, there are exceptions to that, where there is not as much sample available as you would like, and that might cause a problem in terms of how you want to approach this. So in the case of something like an environmental sample, so environmental samples generally, something like water samples, soil samples, typically there is an abundance of sample available. So it's not something you typically have to worry about. If it's water samples, those can be approached very easily. There's typically a lot of sample to work with. Soils, again, a lot of material available for digestion and dilution, etc. So not typically a problem. However, there are always exceptions. So something I was reading recently in a new publication is on atmospheric particulates from Antarctica, for example. So in that kind of situation, what you're looking at is capturing particulates on a filter and then digesting, processing those samples for analysis. And in that kind of case, you're looking at a situation where you don't have very much to work with, and to get the data that you're after, you're most likely going to be working with a limited amount of material in terms of the final liquid volume for liquid sample introduction. The same can be said for biological samples. So common samples that are analysed that are taken from the body, for example, bloods and urines. Again, typically there is an abundance of these. Not always the case, which I'll get to, but typically there is. So that's fairly straightforward to work with. But there are exceptions, again, to that rule. So you've got issues of, you might have issues with something like a tissue biopsy or spinal fluid, where there is always a finite amount of sample that you could have access to then do your analysis with. Geological samples, same again. If you're interested in a whole rock digest, that's going to be something that's fairly going to be not very problematic from the point of view of the amount of sample available. But if you're interested in a single zircon crystal that's got a finite mass of analyte present in it, then that's going to be more challenging. So there is a range, essentially, is what I'm saying. What I'm sure that you're all aware of, that range of availability of sample. In some cases, it's straightforward to handle. In other cases, it's not. So what does that mean for our analysis and our analytes of interest? Well, if you have a sample which contains element analytes that you're interested in measuring that are present at low concentration, then some of your strategies for sample preparation might cause problems. So what is commonly the case is that you do ultimately a dilution of your sample into a final liquid matrix for sample introduction if you're doing liquid introduction. There is a point where if you dilute too far, then you might not be able to detect some of those analytes. In low sample volumes, there might be some issues of the breadth of the analyte suite. So if your interests are a large number of analytes, could that be a problem? Again, same again with the replicate measurements. It's something that we don't want to have to compromise on, but the number of replicates. So these are questions which are generally asked of sample volumes. And again, there's other questions as well in terms of whether you're approaching sample introduction with on an individual level in terms of manual introduction, or whether you're looking at it from a batch point of view with automation. So there's also challenges that could be brought in there. So in the case of automation, there might be very simple physical challenges. So in the case of something as simple as, can you get your sample probe to reach your sample? If you have a low volume, a small amount of sample for introduction, can you actually get your probe to it? So there are questions like that as part of low volume introduction for ICP-MS. There's also something else that I'd sort of like to mention as well in this case, and I've been in this position in laboratories before where and you may have been as well, where somebody hands you a sample of a certain volume, a low volume, and says, what can I do with this? What data can I generate from this? And what I want to do is I want to sort of turn this situation around and really sort of ignore that kind of questioning and look at it differently. So I'd suggest starting with this instead. What do I want? What do I need from this sample? What data do I need from this sample for my study, for my analysis of interest? So I'd prefer to start from that. And this is part and parcel of the idea of working backwards again. So the conventional approaches to ICP-MS in terms of sample introduction So I just got a quick slide on this. So again, this will sound familiar to most people who operate ICP-MS. There really is sort of two main types of sample introduction for liquids to ICP-MS. There's, in terms of automation and batch analysis, you've got automation that operates with the peristaltic pump of an ICP-MS system, so whereby you connect your automation to that system, and that peristaltic pump will pull your sample out of the sample position and continually pump that to your plasma for measurement. This kind of automation is typically pitched to sample volumes at sort of the low milliliter level up to and surpassing, say, the 50 milliliter level. So that kind of automation does a great job. It's a great workhorse type of automation. So it's very robust and does the job that you need it to do. However, in the case of low volumes or a limited amount of sample, there are limitations to that. So first of all, can you get your probe to that sample? Can the probe reach the sample? So that's the first question there. Then you've also got the a question of how the system works with the peristaltic pump. So the peristaltic pump will continually pull sample from the sample position and deliver it to the plasma. When the sample's at the plasma, measurement starts, and that continues until the measurement is finished. But at that point, there's still sample in the line, which will just get sent to the plasma. It's not being having any data generated from it. It just goes through. Essentially, it's being wasted. You've also got the peristaltic pump, which where the flow rate is determined by. It's not a finite flow rate as such. It's revolutions per minute. We do have control over that, but it's still revolutions per minute. And there is, in terms of batch analysis, there's a degree of effectiveness in terms of the pump tubing at that point on the pump. So is the pump tubing in good condition? Is it in as good condition at the end of the batch as at the beginning? So when it comes to low volumes, and if you were running at a lower RPM level, for example, that might affect how your system works for low volumes. Plus, you've also got the waste issue. So, you know, this kind of automation can be stretched to make it work for that, but not always the case. Alternatively, you've also got automation that works with a natural aspiration approach. So that kind of automation would have a nebulizer with a nebulizer uptake line with the probe attached to it, and the automation moves the probe round, and the sample is introduced through to the nebulizer, which operates with the nebulizer gas pulling the sample into the plasma. That kind of automation is pitched to the low milliliter sample volume, that sort of level. But there's limitations here as well in terms of you typically need an excess of sample again. There's still sample wasted in the line after the measurement's complete. And then there's potential issues for things like vapor lock or blockage as well. So it's not quite suited to the kind of application that I'll be discussing today. So something like a blood plasma, for example. So that's the alternative, the second conventional approach. So just in relation to those, I wanted to then introduce the MVX system. So and how this operates for volumes lower than that. But before I get into it, I wanted to come back again to the concept for today. So the idea of tailoring this. So I've already mentioned for the conventional automation, the idea that there's sample wasted. So after measurement is complete, there's still sample in the line between the sample probe and the plasma, and that's for both types of those automations. So either way, there is an excess of sample that is just sent to waste. It basically goes through to the plasma and is not used for any kind of measurement. So there's a wastage there for this, which means that could then affect your the way that you approach your sample in terms of preparation. So going back to this concept here, that what I'm looking to do today is just to walk you through the idea of tailoring to a specific sample volume to get the most data out of a specific volume. And then I'll take you through the MVX system in terms of how this system could handle certain challenges, and then we'll get to the working backwards again. So the MVX system, the MVX 7100 microliter workstation, what is this? What can it do? Well, it's an automation platform for ICP-MS that's focused on low or suboptimal volumes. So what we're talking about here is we're talking about working with sample volumes that you might consider low, so tens or hundreds of microliters in volume, up to what you might call a suboptimal volume, so up to around about 1 to 2 mils of sample. So we're working with that kind of sample volume. The lowest volume that I'm aware of that has been introduced to an ICP-MS was introduced to a multi-collector ICP-MS, and that was 2 microliters. That was the lowest volume that we've generated data from. With those volumes, you can introduce those within a range from 5 microliters per minute, so that's the low end, up to and far surpassing any flow rate that you would ever use for ICP-MS. So typically today, what would be considered like a normal sample introduction flow rate would be about 400, 500 microliters per minute, for example. So it would easily cover that range from the 5 microliters up to and surpassing that and going well into several milliliters per minute and beyond if necessary, but it would cover the full range. So this automation as well is configurable, so it can provide a degree of sample homogenation, sample mixing prior to the introduction step if needs be. There's also an option for temperature control, so samples can be cooled to 4 degrees C if possible to maintain sample integrity through a batch analysis. So if there were concerns of sample evaporation, for example, or any sort of analyte evaporation for something like boron, say. So they can be cooled or they can be heated up to 40 degrees C, so if you require a degree of incubation temperature. Or if you're working with something that has a low solidification point, that kind of temperature control would be useful. It's also capable of piercing a vial septum, so if you're interested in septum piercing, this system can work with those kinds of sample vials. It's also compatible with weld plates, so both 96 weld plates and 384 weld plates, up to a height of 44 millimeters, so it can cover the low capacity wells up to the higher capacity wells as well. And we can configure the rinsing processes to make sure that the system is focused on making sure it's operating in the best way for the measurements that you're undertaking. So if you've got analytes that you're interested in with no memory effects, then we can configure the rinsing processes to make sure that the system is returning everything back to baseline as soon as possible. So a tour of the hardware. So this is the system as it is. Now, I mentioned that I'm the product manager for the 7000 series automation platform. So the central piece of automation here is one of our ASX 7100 auto samplers. So this is an accurate and precise XYZ auto sampler. So it's got the precision to be able to sample from a 384 well plate. And if you've ever worked with one of those, you'll know that those well positions are very small and they're very close together. So it's got that accuracy and precision, so it will reproducibly do that if required. Attached to this automation, or it doesn't have to be attached, associated with this automation, there are 2 syringe modules. So one of them is what we call the valve syringe module. So that has a short sampling syringe. So if you can see my cursor, it's this one, this short sampling syringe here. So this syringe pump is responsible for pulling sample up from the sample position and pulling it onto a sample loop, which is attached to this 6-port switching valve, which is the other component of this valve syringe module. And from there, the sample is then delivered to the nebulizer from that point there. So because this is ICP-MS, all of the components are metal-free, so the materials in the liquid-facing flow path for this system are manufactured of quartz, PEEK, CTFE, and PFA. So it's the sample probe, which is quartz. Now, the other syringe module here is what we call the syringe pump module. So this is a tall syringe. Now, this takes place essentially of your peristaltic pump for the sample introduction process. So this will push the sample off the sample loop to the nebulizer. And again, metal-free flow path. Now, these two modules can be mounted on either side of the automation, or they can be sat together, either way that you want to use it, and depending on the ICP-MS instrument that you're operating with. So how does this work? Well, I've sort of alluded to most of this actually as we've gone through, but you've got the automation, the ASX 7100 automation on the right hand side here, and then you've got the two modules. So essentially what you've got for the introduction process is you've got two parallel flow paths. You've got this one in green here. So you've got one end, you've got the sample probe, and follow that line, it goes through to the 6-port switching valve in the sample loop, and then follow it to the end, and you've got this small sampling syringe. So when the sample probe goes to a sampling position, that short syringe will pull the sample up through the green line onto the sample loop. So that's where we position the sample ready for introduction. At the same time, there is this other flow of liquid along the blue line. So this syringe pump module will push carrier solution through via the 6-port valve and then through to the nebulizer. So these two processes are happening at the same time. When the sample's on the sample loop, then that valve will switch and it will bring that sample into that flow. So what you've got is essentially, so the line color changes here, but the syringe pump module will push carrier solution to the 6-port valve through the sample loop, and it will push that sample off to the nebulizer, and it will introduce it to the ICP-MS at that point. And then again, in parallel, while that's happening, this short syringe will backflush and clean the line through to the sample probe into a rinse station. So that's one aspect of the rinsing, and then the other one is that an excess of carrier solution will clean the sample loop behind the sample and deliver that to the nebulizer. So that's how the system works. Now, I mentioned that, nebulizers, compatibility with nebulizers. So the system is compatible with most nebulizer types. Now, I say most because so far I've not come across one that it's not compatible with, but there may be one of those days. So as I mentioned, the system is compatible, will deliver a flow rate from 5 microliters per minute up to and far exceeding anything you would need for ICP-MS. So it will allow you to operate with any kind of nebulizer over the flow rate that you would require. So basically everything from total consumption nebulization up to what you'd consider everything you would need for standard ICP-MS nebulization. So how does that help us tailor the introduction process? So in terms of low volume sample introduction and low flow rate sample introduction, I could talk a lot about this, but there are 3 main areas that you could look at in terms of advantages of doing this. But the one I'm going to focus on today is basically generating the maximum amount of data, so the middle one, the maximum amount of data from the sample volume that's available. So hold on a second. So, there we go. Okay. So generating optimum data, the most amount of data from the sample volume. So at this point, what I want to do is I want to just go back quickly to that idea of that question that I prefer to be asked. So not what can I do with this low volume sample or what data can I generate from this, but more what do I need? What do I want from this sample? So if you ignore the actual volume to start off with, just start there. That's the starting point that I would suggest that you make here. So really what this comes down to is all about measurement time. So if you start with that question, what do I want? Then you can start tailoring this process. So from the point of view of measurement time, we come to the point of these questions. So what do I want from my sample? What kind of data do I want? How large is the analyte suite I'm interested in? How many analyte elements and isotopes do I want to measure? How many replicant measurements do I need? Do I need 3? Do I need 5? Or do I need more than that? For quadrupole ICP-MS, are there different collision reaction cell gas modes that I'm interested in? Is there one of those? Are there several of those? Do I need to repeat the analysis? Do I need to do this several times? Do I want to repeat it again and do a clarification analysis? That kind of thing. So it all comes down to, when you ask these questions, that gives you an indication of the measurement time that I need from this sample. And then from that point, you can take this forward. So if I know the measurement time required for this, with the MVX 7100 system, we've got the control over the sample introduction flow rate, and we can work with specific sample volumes rather than continual pumping. We can take a finite sample volume of our interest. So that gives us the flexibility to tailor the whole process. So before I move on to the specific example of blood plasma, what I wanted to do is just to show you, just I suppose in a more of a visual way, in a graphical way really, what this actually means. So in terms of having that flexibility. So what you're looking at here is you're just looking at a series of traces. So TRA traces of data from a multi-element standard, just a 1 ppb standard that I'm sure you'll all be familiar with. 100 microliters of one of those 1 ppb standards has been introduced via just a typical 400 microliter concentric nebulizer. So nothing special about that nebulizer, just the standard kind of nebulizer you would see in a lab associated with an ICP-MS instrument. And all we've done is we've introduced that 100 microliters of multi-element standard at different flow rates, different introduction flow rates. And what you can see from there is the effect on measurement time. So if we start with the top left trace, what you're looking at there is the introduction of 100 microliters of standard at 200 microliters per minute. And after the wash-in time and that point where the signals are stable, that gives us about 21 seconds of measurement time, which is great. But if we want more than that, we can do the same again with a lower flow rate. So if we go to 150 microliters per minute for the same 100 microliters of sample volume, that gives us 31 seconds. And we slow it further, we take it to 100 microliters per minute, and we're looking at something like 48 seconds. So you can see the trend. We have that capability, that flexibility to stretch out the signal data. So you drop it further to 75, and now you've got more than a minute of measurement time from 100 microliters. Stretch it further to 50 microliters per minute, and you've got a minute 43. And we're not even at the bottom end of the introduction flow rate. We're not even into anything like a total consumption nebulization system. This is all with the same standard, typical concentric nebulizer that you would typically work with. And what you'll find is that those kinds of nebulizers are actually very forgiving to flow rate. So you've got a lot of flexibility to work with that. So that's sort of what I wanted to just show you quickly before I move on to blood plasma specifically. So I've used blood plasma as an example here, and I don't have data specifically as such. And what I wanted to talk you through was the sort of the method development process for this. Now, the thinking behind this actually comes from a study that is ongoing at the moment down at the London Metallomics facility at King's College London, where we've been supporting this process with the laboratory down there for a specific limitation of sample that they have available. So I just want to walk you through this thought process essentially, that's actually a real world thing. So blood as a sample generally. Well, whole blood, blood plasma and serum, it's a commonly analyzed sample type. It's not just associated with analysis by ICP-MS, as I'm sure you all know. There are numerous different types of analysis undertaken on bloods. ICP-MS analysis is just one of those. It's an easy sample to take. It's the kind of thing where it's easy to take, you know, fill a vacutainer with something like 10 milliliters of sample. Multiple vacutainers can be taken. If anybody's ever donated blood, you'll know what that's like, where samples are taken during that process. In terms of ICP-MS, the analysis is mainly focused on things like establishing nutritional status, so establishing the level of certain elements to determine health or whether there is an issue of deficiency. Selenium is a good example of this. So in certain parts of the world, some people can be deficient in something like selenium, and that is represented in the level that's shown in the blood. So that's a good example of that. Contaminant elements, for example, lead or arsenic, measurements from a contaminant point of view, is also a common measurement. So this is where ICP-MS comes into this. And in terms of the analyte concentrations that you might be interested in measuring, this is actually very broad for this sample type. So depending on the analyte, you're looking at concentrations down at the low ppb end. So if you're interested in measuring something like cobalt, chromium, selenium, that's down at the low part per billion end. If you're interested in measuring zinc, then it's going to be at the other end of the scale, sort of at the low part per million end, so milligrams per litre. So it's an interesting sample to look at, because you have to consider all of those elements that are present, and your sample preparation processes to make sure that you don't dilute too far. You might do a digest on it. There's multiple ways of approaching this. So as a sample, that's why you might be interested in looking at it with ICP-MS. Why might blood or plasma and serum be limited? Why might you only have a low volume? Typically, if you were to work on individual levels, that it may well not be. But there are exceptions to this. So, for example, there might be legal restrictions to the amount of sample that can be taken. So, for example, if you are taking samples as part of a study on children, infants, babies, there are legal restrictions to the amount of sample that you can take and then operate with. There's another consideration here, which is the one that I'll be mentioning about our work with this study at the LMF, and that is sample splitting. So if you're working with large studies or trials, even with a regular amount of sample that is taken from somebody, if you're subdividing that sample into subsamples for analysis, then you are going to be left with smaller volumes, which are then spread out over multiple techniques. That's the case here. And in this case, you're looking to generate as much data as possible from the sample that you have available. So those are the two key reasons. That I'm sure there are others that I've not considered, but sample splitting is the one I'll be focusing on next. So in terms of what we're looking at here, in terms of a large study and sample splitting, I've mentioned numerous techniques might be involved. So things like routine biochemistries, determination of glucose level, vitamin D, etc., that kind of thing. Those are regular measurements. Trace element analysis, I'll be getting to NMR measurement for metabolites, mass spectrometry measurements for lipids, structural content, etc. There's numerous things that you could be looking at. For trace element analysis, this is where we come to working backwards. So I'd like again to start with what do we want here with this kind of situation. In some analyses, you might well be focused on certain measurements. So, for example, a common measurement on bloods and blood plasmas might be something like, from a nutritional point of view, it might be copper, zinc, selenium. That's a common one. Or it might be focused on the contaminant elements. But there might be a specific focus on a handful of elements. It might be 3 or 4 elements that you might be interested in. It might be a full screening, or as much as possible screening of elements that are present in the sample. And that's more the case here. So in the case of the work that's going on down at King's College, we have, after the sample's been split, we have 250 microliters of sample available to work with. So that's blood plasma. So that's before any kind of dilution's been done or anything like that. Now, the analysis requires as many elements as possible, but we've decided on 45 analyte isotopes to be measured. So that's what you can see on the left here. So this is a screenshot from PerkinElmer operating software. So what I wanted to show you here was just the list, essentially, of the analytes of interest that are looking to be measured. There are 3 different sets of collision reaction cell conditions here that are factored into this. And there's a requirement for 3 replicate measurements. So as a result, the actual measurement time from all of this put together is 4 minutes and 48 seconds of measurement time. And that's with this particular PerkinElmer instrument. It will be different depending on which type of ICP-MS that you have. But the idea behind it is the same. You end up with a specific amount of measurement time. So what we're looking to do now really is to marry up the measurement time with the sample that we have available. So anyway, 4 minutes, 48 seconds. So like we all do, we all like to work with round numbers. So what I've thought to do then is, let's say 6 minutes. Let's work with 6 minutes. Let's start there for the sake of this presentation. Let's say that we need 6 minutes of measurement time, just so that we've got a buffer either way. Now, this looks, very simple equation here. So the idea of the relationship between the measurement time that we need versus the sample volume and the introduction flow rate. So divide the volume by the flow rate, we get the measurement time. So we're looking for 6 minutes. So what we can do at this point is we can start asking a few questions. So what's more important to us? Is it the volume, or is it the introduction flow rate? Are we interested? Do we have a very, very small amount of volume and we have to work to that? That could be the thought process here. Or it could be, from an RSD point of view, I need a higher flow rate. I'm not looking for total consumption. I'm looking for a relatively high flow rate, and maybe we've got the degree of flexibility to work with the volume. So that's the kind of thought process here. In this case, I'm actually, with 250 microliters of sample available, I'm not that concerned about the volume. So, and for the sake of argument here, I'm just going to start with 100 microliters per minute of introduction flow rate. So for 6 minutes, we're going to need 600 microliters of final sample volume to work with. So after sample's been diluted. So great, 600 microliters, we can get our 6 minutes, no problem whatsoever. So again, we're working backwards. So what does that mean for our sample preparation? Well, in this case, we're just doing, because it's blood plasma and not whole blood, we're going to do something simple, and we're just going to do a 10x dilution of the blood plasma with a 0.1 molar nitric acid solution. So that's the way we're going to approach this. There are numerous other ways of handling this. There's different medias to work with for dilution. Some people do go about this with a digestion, then a dilution. There's multiple approaches, but the argument is the same. So if we need 600 microliters of sample solution for the introduction process, then we can take 60 microliters of the blood plasma sample, dilute it 10x, and then we can proceed from there. We've got 250 microliters of sample available, so we could do this multiple times if we like. So we can, we could scale that up if we wanted to do this twice, no problem whatsoever. So that's the way we would approach this. And then in the case of how we're approaching this at LMF, we're doing this in sealed vials, so relatively low volumes for batch analysis. So we maintain the integrity of the samples in sealed vials, and we pierce set to take our sample and do the introduction from there. So we make sure that there's no issue with evaporation, etc. Now, as I mentioned, we've got this flexibility to work with. So if we need 6 minutes of stable measurement time, we can really make this work in our favor. So if we want to work with less sample, then to get our 6 minutes, we could reduce the introduction flow rate from there. So for example, if we reduce the flow rate to 50 microliters per minute, all of a sudden now we only need 300 microliters of sample volume for introduction, which means that we would need 30 microliters of the actual sample itself before dilution. So there's a lot of room to work. Similarly, we could go in the opposite direction, and if we're not that concerned of that kind of volume, we could go to a higher flow rate, so 200 microliters per minute, and work with just a 1.2 mil of sample, so 1200 microliters. So we could go in that direction as well. So we've got that flexibility for this introduction process. Now, also, this is a broadly applicable concept. So it doesn't have to be blood plasma, blood urines, whatever. If you had a sample biopsy, a tissue biopsy, for example, and you did a digest on that, and your interest was something with a low concentration of analyte that you're interested in measuring, then you could approach this in the same way. You do your digest, you prepare everything in a low volume, and then again, like I said, you work backwards to make everything work for what your interest is. If you've, regardless of the way that you work this, if your interest might be different here, it might be instead of a large analyte suite, it might be, well, I don't want to lose that low concentration analyte to the dilution process. So I want to work with a lower sample volume to make sure that after I've done a digest, the concentration per unit volume in what I'm introducing is higher, so the signals are higher. So we've got that flexibility to work with this and get the best data that we can from the sample. A spinal fluid, again, that's something which has been mentioned to me in the past. Something like that is always going to be a limited amount of liquid available. So with the arguments the same. We use the same process for things like zircon crystals, so single crystals in geology via multi-collector ICP-MS. The process is the same. We've done the same with petrochemicals, for example, diluting low volumes of research crude oil in xylene. The argument's the same. You work through this thought process backwards. Start with what you want, and then you work it through to the preparation process. So it's broadly applicable across any kind of analysis with ICP-MS. So like I said, I didn't want to focus so much on data for this presentation, more the thought process behind this. So I just wanted to sort of leave it there for today, but just sort of some general conclusions for you. Really, I wanted to leave you with the idea of, from this sample, I want to achieve this. You know, I want this data. This is what I want to generate from my ICP-MS instrument for my study, for my analysis, rather than looking at something and saying, what can I do with that? Because of the capability of the most current generations of ICP-MS instruments, the detection capability, the sensitivity is now available for us to do a lot of work on the sample introduction end, certainly with low volumes, to get more out of what previously might not have been possible. So that's why I sort of wanted to leave you with there, that idea of looking at what do I want from this rather than what can I do. And then the MVX 7100 system being employed to really tailor that introduction process and address the challenges posed by some sample volumes or sample masses in your laboratory environment and with your ICP-MS instrument. And then this has been something which has been said of numerous different applications and sample types, and that's that the MVX 7100 system really has opened up the opportunity for analysis with low volumes or suboptimal volumes. So opening up the ideas of measuring certain things that haven't been reachable before in low volumes, and blood plasmas and certainly analysis in the geological fields has really shown us that so far. And just some final acknowledgements. I want to say a big thank you to Thea Stewart and Alex Griffiths of London Metalonics facility down at King's College. And I want to thank you all for your time. And if you've got any questions, please feel free to either ask them now, or you can forward them to my email address here, and I shall get back in touch with you from there. So thank you very much for your time.
Pete, do you see the questions that are in the queue?
Carryover issue. Rinses between samples. So yes, like any other automation, you would always do rinses between samples. So you would always do that regardless. But it's down to the operator, so you as the operator, as how you would handle that. So as I mentioned, there are two parallel flows to this. So let me just show you quickly, go back to one of the previous slides, if it will let me. So one of the previous slides on the two parallel flows. Here we go. So what you've got first of all is, whilst the sample's being introduced, so during this point, the tall syringe is pushing the sample off the sample loop towards the nebulizer. So whilst that's happening, the other syringe is washing out, so it's back flushing through the sample probe to the rinse station. Now that process, this back flush process, rinsing process, actually takes place and is finished before the measurement process through the nebulizer is complete. So that does take place as you typically would, cleaning, rinsing, but it doesn't add any time to the process. And then the other process is you push an excess of carrier solution to clean the sample loop behind the sample. And again, that's down to the operator. So you could push as much or as little additional carrier reagent to the nebulizer as you would like. So if you were so inclined, you could do that as a minimum and push the sample off so that that's just done. if there is not a requirement for pushing a large amount of liquid to rinse through. But if you've got an issue with a memory effect or an analyte where it's known to have memory effects, or something which is present at a high concentration and you'd be concerned about carryover, then you can address that in that process. There's also a means as well of configuring the system so you can actually just, at the introduction flow rate, you can just push the sample off the loop to the nebulizer, and that's the analytical side of things. And then before the next sample is pulled up and introduced, you could do what you call a quick push, where you push a large amount of carrier at a higher flow rate through the nebulizer, so it washes that loop through again. So you've got that flexibility to do this, but all of that is handled as part of the introduction process, and it's factored into the introduction process for each sample. So it's a long way of me saying yes, you run rinses between each sample. Well, I've got a fair few questions here. Hang on a second. So I'm just trying to. Okay, so loop size, that is entirely down to the operator. So what is typical is either a 500 microliter loop or a 1 milliliter loop, but it doesn't really matter. If you run something, if you put something like a 1 milliliter loop on there, the way that you work this is you don't completely fill the loop with sample. You bracket the sample either side with a small air gap, and that's how the system works. So everything is primed on the system. So the uptake line is primed to the end of the sample probe, and the syringe pump module through to the nebulizer is primed as well. So basically, it doesn't matter what size of sample you're pulling onto the sample loop, as long as the size of the sample is not bigger than the loop itself. Also, sample loops are just tubing, so you can adapt those to your requirements. So if you need something bigger, then you can adapt that in your laboratory and attach it with the same fittings and ferrules. So that's an easy, that's a straightforward approach to this. Right, where are we? RSD issue. So low flow. So that's a very good question, actually, RSD for low flow. So obviously, what I did mention here is, allow me to do this. So if I just go to the traces for a moment, so what you'll see here is that's a really good point on RSDs. So if you were to stick with the same standard nebulizer here, the 400 microliter nebulizer, and you introduce at different flow rates, what you'll see is that if you ultimately went down and down and down the flow rate range, let's say that you dropped it down to, say, 10 microliters per minute, and you passed it through a standard 400 microliter concentric nebulizer, you would expect the RSDs to worsen compared to running it at something like 100 microliters per minute. So what you would do at that point is, if you were going to work at very low levels, then you would use a more appropriate nebulizer to that. But what we have seen is that for this kind of nebulizer, something quite typical, a typical 400 microliter nebulizer, concentric nebulizer that is, that the RSDs are actually still very good regardless of the flow rate that you're working with. So that's actually something that I can share with you. So if you, I can follow up with you with some data on that, because that's something which has been provided to me. I just didn't put it in this presentation, but it's a very good question. But again, it's part of how you would tailor your introduction process. So for very low flow rates, you would probably look to working with a different nebulizer, but generally, standard nebulizer is probably going to be fine. Dilution. So dilution, this is, you wouldn't use this system for dilution. So if you're doing a prep, you do your prep manually. So for this, there is a degree of dilution capability with one of our pieces of operating software, but it's not typically done. So no, dilution is done offline, and then you use the automation for sample introduction for this. So this is you're looking to do this offline. Carryover issue. Okay, so I've answered that one. Was experimented with total consumption introduction systems. Yes, we have. So we've gone all the way down to the total consumption nebulizer arrangements here. So in that case, because of the low introduction flow rates, you would set that up with a short nebulizer line between the 6-port valve and the nebulizer attached to the ICP-MS. So yes, this can go all the way down to 5 microliters per minute introduction for total consumption. With the DS5 nebulizer that we manufacture, the DS5 total consumption nebulizer, the sweet spot for analysis is 7 microliters per minute. So you could use that. The single cell glassware from glass expansion, yes, also works with that. So similarly, single cell analysis, from what I have seen in terms of flow rate, best operates at somewhere just above total consumption. So you're looking at somewhere between 10 and 20 microliters per minute. But yes, this system will work with that. On single cell, we do know that this system works very well with cells. So we know that cells are 95% still viable as they are leaving the MVX system. So we know that that's the case. We've seen that done through testing in Japan. Where you might lose cells to cell lysis through the introduction process is actually in the nebulization process primarily. So yes, that can work. The MVX can work with those kinds of nebulizers. Yes. Loss of sensitivity between that. So loss of sensitivity. So that's not actually something I've actually measured between that kind of level. That is a very good question though. There is a degree of sensitivity loss, obviously, because as you stretch out that sample, you are, the payoff is a degree of lowering of the sensitivity. But as I mentioned, because the most recent generations of ICP-MS are more sensitive, because there's so much more sensitivity from those instruments, you do have that much more flexibility for this. So you've got so much more flexibility to work with lower volumes and stretch that out. Yes, you have a degree of sensitivity loss, but because of the sensitivity capability of ICP-MS generally, then it's less of a concern. But if that's a concern for you, if that's a question that you want more information on, I can reach out to some customers and collaborators and see if I can get that information for you. I think that's all of the questions, I think. Are there any other questions for today?
No, I think that's all the questions we have, and we are right at about an hour, so we should go ahead and wrap up.
Perfect. Brilliant. Well, thank you very much for your time, everybody, and I hope that this has been worth your time. So thank you very much for attending. Thank you.